and somehow maximize my slides. Okay, hi everyone. So I guess the one thing maybe I wasn't effective enough in advertising the fact that we should strive to do better mutual information estimation was the point we ended on last time, and here's a link to the code. What I want to do for I think most of today is sort of deliver on two of the things that we talked about. One is together another measure of information that arises naturally in establishing fundamental limits on communication, but that we can sort of look back at retrospectively and say and agree that it's very natural statistical inference at large, and therefore ask ourselves how can we estimate it, and bring another theme that I promised we would discuss, which is use a lot of the know-how, both theoretical and algorithmic, from the world of universal compression for other sequential decision-making problems, such as the estimation of things like directed information. Okay, so that's roughly what I want to do today. So what is directed information? Many of you are familiar with this creature. The direct information between goods from an n tuple xn to a y tuple yn is defined to be the sum over I from 1 to n, mutual information between x up to I, x1, x2 up to xi, and yi given the past ones. Okay. So if you want to compare this to mutual information, right? So as we recall, the chain rule, mutual information that was mentioned in several different contexts, several different lectures yesterday. One way of expressing the mutual information between this pair of n tuples is as a sum of mutual information between x, the whole x n tuple, right, and y and I in the past ones. The difference is, so the only difference is that here we have x only up to pi I. So obviously, by data processing, mutual information is more an upper bound on the directed information, and in many situations, it's much larger than the direct information. And where this direct information arises, why do we care about it? So again, many of you know that direct information arises in the characterization of fundamental limit on reliable communication across a very broad range of channels, in particular in the presence of feedback. So for feedback communication, and in fact, in general, for communication, it turns out that the right quantity actually to look at is, in fact, direct information rather than mutual. Okay, so many of you know the classical stuff. The classical results about, let's say, the book of Gallagher, broad classical channels, they all finite state channels, essentially all finite state channels and composable channels. There's a whole chapter in Gallagher's book that tells you that the capacity is, essentially, C is, right, so you maximize over mutual information between the input n tuple and the resulting output n tuple, right, normalized, you maximize over all the possible input distributions, and you take a limit, and that's the capacity. And the reason, and this is in the absence of feedback, and really the reason why mutual information arises here is that In these channels, essentially, the real quantity we're trying to get at when we sort of move from given code and sort of an operational performance to a sort of an informational characterization, the key thing that we rely on is that the mutual information between the message and the channel output, right, is the mutual information between what you put into the channel when this is the message, so xn is xn of m, and the channel output. Okay, and because of that, and this is true in the absence of feedback, okay, and it's not necessarily true when you have feedback. Right? So, for example, think of a very extreme case. Let's say you have a BSC of crossover probability a half. Right? Obviously, so this is the input, and so this is the output. Obviously, this is a useless channel. The mutual information between the message and the channel output for any scheme is going to be 0. Right? On the other hand, if you had feedback in such a channel, let's suppose you use this feedback in a trivial way, and you let, say, the channel input of I be the previous right? Then what is the mutual information between x and yn? Right? Well, it's essentially the mutual information between y up to n minus 1, yn, the entropy of the noise through this channel. So essentially, up to n or n minus 1 is essentially n is increasing linearly with n, essentially n times 1 on the entropy of renewably half variable density noise. Okay, so in the presence of feedback, you can get a lot of mutual information between xn and yn, and that's obviously very, very different than the mutual information used between any message you're trying to communicate and the channel output. Okay, which in this case is obviously 0. Right? But it's always the case, with or without feedback, that the mutual information between the message output is the directed information, in fact, between what you end up inserting into the channel, right? Which in the presence of feedback, x of I will be a function of the message, and the y is up to I minus 1. Okay, the direct information from whatever you end up putting into the channel and the channel output. So this is always true, in complete generality, under any scheme, with or without feedback. Okay, so just so happens that in the absence of feedback, you have this, and therefore this result is valid. But in general, for the feedback, the right characterization of the right functional that comes up is direct information. Okay? And so this is a very general characterization for a very general set of channels, and there are different works here that assume different sort of families of channels. And sort of the maximization is implicit. So here, in the absence of feedback, the maximization is over distributions of this type, which you can sequentially distributions of this type, xi given past xi's. More generally, in the presence of feedback, you're going to have a maximization of the form of distribution on xi given the past xi's. But in any case, so there's a whole body of work, and these are some of the initial papers in this direction, and subsequently, there's been much activity on trying to characterize and explicitly compute these things for all sorts of interesting channels. And so this is not just sort of in the law land of multi-letter characterizations. This is not just sort of a formula that no one cares about. You can actually explicitly compute it for many interesting channels. But as I said, this is not the point of my lectures. My whole point is that we have something that comes up as an answer to an operational question. But now let's look at why it might be interesting more generally for problems outside of communication. We just care about inference. So consider a scenario of you have these two processes, two signals. They're maybe perhaps they're evolving together. Let's even suppose, for completeness, that there's a certain sort of ordering of time. So maybe first there's x1, and then comes y1. Then x2, then y2. Then x3, then y3, and so on. Okay, so you have maybe a pair of processes, pair of phenomena that are evolving together and you care about. And let's say that one thing you, okay, so maybe you want to do inference on the y process. Maybe y represents some stop data that you care about. So you see, the past performance of this stop up to say I-1. You want to do inference on y times I. And so at your disposal is again the past of the y's and the past till present of the x's. I'm assuming that yi comes after xi. Okay, so I want to do inference on y times I. I have the past of y up to I-1. I want to know to what extent everything that happened in the x process so far is of relevance. Of relevance as I try to infer y. Right? Now, the whole point of the big point of the previous lecture was that we have a natural, in fact, we have essentially only one natural measure of statistical relevance of one phenomenon to another. Right? We agree that is the mutual phenomenon. And so, to quantify to what extent I should be looking at, if I want to do inference on the y process, given its past, right? That's exactly what we agreed should be the mutual information. So how relevant is everything that happened in the x process so far if I want to infer y times I given the past of the y process? The mutual information is the only natural measure of relevance. And similarly, if I want to, say, do inference on x times I, given the past of x, to what extent should I be looking at everything that happened in the y process so far? Right? Again, everything that happened in the y process here is y from 1 up to I-1. Right? So to what extent? Well, the mutual information captures that. So given the past of the x process, how relevant is everything that happened in the y process so far? For inference on x times I, that's measured by this. And so when you sum these guys up, right, what you get is the directed information from x to y. You sum these guys up, you get the direct information from y to x. Here, this is sort of my way of writing this shifted one to the right. It's y up to n minus 1. Right? So we have y at I minus up to I minus 1. Okay. So, and so again, this directed information, right, is a very natural in ways that are analogous to those that we talked about. How mutual information is the only natural measure of relevance. Well, this is the only natural measure of the degree to which, again, the x process is of relevance when you try to do inference or sequential inference on the y process. Okay? To what extent should I be looking at the x process if I try to do inference on y? And some people take this slightly further and say that it's a very natural measure of sort of causality. To what extent is the x process involved in driving the evolution of the Y process. But that maybe is a little bit charged. Many people, use causality as a charged word. Here I mean, when I say causal, so I'm not going to engage in any philosophical discussions. When I say causal, I mean sort of just causal inference. I want to infer why I based on the past. Why? To what extent is everything that happened so far in that process? I'm not really engaging in the discussion. Is whether this being high means that X is actually driving the evolution of Y. Okay? In many contexts, it is natural. But again, what we can agree on is that if this is high, then I should be looking at the X process when I try to do inference on the Y process. One exercise, I think this is an exercise I'm going to give you. About 4 lines playing with very basic chain rules of information theory that we've seen in some of the previous lectures, that we always have this, what I call it conservation law. So the mutual information from between X and Y process is always the directed information from X to Y, and plus the direct information from Y shifted one to X. So again, it's if you want to think of direct information as sort of this notion of X is sort of causally involved in the evolution of Y, then this is a really nice sort of quantification of the sort of so-called correlation versus causation question that many people, in many statistical experiments, often there's, okay, one thing is correlation, the other is causation. Well, here you can see that sort of, this is a kind of correlation. The overall statistical dependence between the X and Y phenomena is decomposed into, in a sense, the degree to which, if you will, X is responsible or causing or responsible for the evolution of Y, plus the degree to which Y is causing or driving the evolution of X. Okay, so the main thing I want to cover at least this today is talk about some approaches for estimating the direct information, or so-called direct information rate, in sort of classical but still interesting and practically interesting setting of stationary finite alphabet processes. Okay, so when X and Y are jointly stationary, it's not hard to show that this limit exists, and it's known as the directed information rate. We would want to learn it from data is because we want to know to what extent one phenomenon is relevant for the causal evolution of another. And again, getting back to one of the main things that I talked about in the abstract, I'm going to want to do this to come up with estimators that are based on universal compressors. And so, again, I'm sort of assuming that most of you are really closely familiar with lossless compression, and so you know well that there's really sort of one-to-one correspondence and potential equivalence, right, between a lossless compressor. And a lossless compressor really defines a probability, whether it wants to or not, right, by the Kraft inequality. Essentially, a lossless compressor always responds to essentially a probability on the data that was designed to compress. And if we're talking about sequences, right, any law sequence, I can always express in terms of conditionals of one component given the past. Right? So any law on the data is equivalent to a so-called sequential probability assignment, which is the way to express it in terms of conditional probabilities. And this then also implies that If you have a universal compressor, which many of you are familiar with universal compressors, those are guaranteed at any say the entropy rate of any stationary process, then they induce universal probability assignments, which are equivalent to universal sequential probability assignments. So to be slightly more concrete, let me take one definition of universality, which is, so we're going to talk, so again, I'm moving back and forth between the lossless compressor and a law on the data. Lossless compressor for a sequence and the law on the data that corresponds to it. So a law Q on sequences is universal if the normalized relative entropy between sort of the true law on the first n components of the process and the law under Q is vanishing or any stationary law on the data. And there's a slightly stronger notion, so-called pointwise universality, which is that I don't even need to recall, right? Relative entropy is by definition an expectation of a log of the likelihood between P and Q. In fact, even there's a notion of pointwise universality where I don't even take the expectation over the log of the likelihood. I just look at the normalized log of the likelihood, and if with probability 1, this is converging to 0, if you want to be fancy, you can say within soup, no more than 0, there's actually converging to 0. With probability 1, whatever the stationary and ergodic law which governs the data, then this is known as pointwise universality. Again, some of you are familiar with the notion of ergodicity. Those who are not, don't worry about it. And let's just focus on, and we can just focus on this definition of universality. But for many of us, by now we take for granted, this is classical stuff, the existence of universal compressors that achieve the entropy rate of any stationary process, which is equivalent, by the way, to this statement, right? Because if you have, again, a compressor that achieves the entropy rate, it means that the Q induced by the compressor is such that its excess number of bits over the entropy, which is this relative entropy, right, will normalize sequence length is vanishing. So this, so I hope you're with me that this is completely equivalent. So the existence of a Q, which is universal in this sense, is equivalent to the existence of lossless compressors that achieve the entropy rate of any stationary process. And this existence is, again, by now a pretty classical fact in information theory, and I definitely encourage you guys to look up over in comics such schemes as Lempel zip, so Lempel zip compression, is a very good example of a scheme. CTW, contextual weighting, is another celebrated example. These schemes are nice because they're very sort of computationally, algorithmically graceful. And again, you can prove that they are universal in the sense of achieving the entropy rate of any stationary process. In fact, CTW is, in many ways, it's even more celebrated than well, okay, like that, some more celebrated. In terms of analysis, so-called redundancy rates, right? So how quickly is this convergence happening? That is, sorry, for the contextual weighting algorithm, in fact, it can show that, so that not only is it universal, but it has essentially optimal convergence rates. And what I mean by that, again, some of you are familiar with the notion of lower bound, right? So listen, lower bound tells you that if you're trying to, say, compress with respect to a parametric uncertainty set, then there is a certain rate at which the redundancy, this normalized relative entropy, can convert, can vanish. In fact, that rate is essentially K, which is the dimension of the parameter space over 2 log n, and normalized by sigma. So that's a leading term. All you care about is universality, not with respect to all stationary processes, but with respect to some parametric class of sources, parametric dimension K. Like for example, if you care about only IID sources on an alphabet of size, the size of the alphabet, then the effective parameter space is the size of the alphabet minus 1. By the probability, you have basically size of the alphabet minus 1 free parameters. That would be K. So x minus 1 over 2 log n over n is the best redundancy rate that you can get if you care about universality only with respect to IID sources. In a very strong sense, it's achievable, but there's a very strong sense in which this is also a lower bound. Can't be better than this. In fact, not only in some sources, but on most sources. Again, some of you are familiar with this, and others, I will encourage you to look up, listen, and lower bound. So in any case, context tree weighting is a scheme which I also encourage you to look up, and you can look at one of the a few ISIPs ago. There was a whole lecture, a whole plenary lecture by Willems, one of the inventors or discoverers of this algorithm, that was dedicated in a very lucid manner to just exposing this algorithm. It's sort of how they stumbled across it, and how you can sort of implement it very naturally. And so you can look it up. But what you can show in terms of analysis is that it achieves the the resonant lower bound on every tree source. So you don't even need to know what sort of the active tree might be. Whatever the tree source, the true tree generating the data might be, you're guaranteed of achieving the resonant lower bound as if the tree were known. Okay? And again, algorithmically, very gracefully, linear complexity, and so on. Okay, so universal lossless compression is, again, the take home is that it's a problem which has been studied very extensively in our community, and you might say many will argue it's largely solved. In the sense that if you come to some conference now or a new universal lossless compressor for finite alphabet stationary sources, no one's going to care. But in any case, but if we have that, one of the points I was trying to make is that we can use this for other sequential probability kind of problems. One is in the context of prediction. So if you will recall our the Pinskers inequality, in fact, maybe also inspired by the other speakers, maybe I'll also do some whiteboard.
There are better pens over there.
Oh, okay. And is there? Oh, thank you. Okay, so I want to give you a taste for how, say, a universal compressor induces a universal predictor. Because this is pretty easy, but it already has many components that we use the schemes that I'll show you later for estimating directed information. So what I want to, let me start. Okay, so I'm going to, let me recap some of the things that we've seen in the first lecture and some of the other instructors' lectures. Right, so one thing was the total variation distance between two probability laws, right? Very generally, two arbitrary probability measures on an arbitrary measure space. That's defined quite generally as a supremum over all the possible events of probability the event under P minus the event under Q. And for us, this is also equal to 1/2 simply the L1 distance between the probability vectors when these are, so in the special case where P and Q are PMFs, okay, on the discrete alphabet X. Right? So then P and Q are PMFs, total variation is essentially up to a half, which is the L1 distance between the probability vectors. And one thing that we call, right, so we call that we have the Pinsker inequality, which is that total variation distance between P and Q is upper bounded by, we have a half in here, relative entropy between P and Q. And so now connecting to one of the things we talked about, which was sort of estimation, we had that if you give me a loss function from, let's say you want to estimate something that lives, let's assume the finite alphabet X, and so you want to estimate your estimation space, the space of possible guesses for X is in general maybe a different one, X hat, have a loss function. Then you can talk about the expected loss in estimating X or guessing X with any possible guess value X hat. And when X, let's say if when X is distributed according to some law P, right? And so you can talk about the best expected loss in guessing X under the loss function L. So we're going to minimize over all the possible guesses, and this is often called in literature the Bayes response. So this is the Bayes response associated with a given loss function to a distribution P. So let's say the arg, right? So if you give me a distribution P, X hat Bayes is that value that I should use for guessing X if X is distributed P. If I want to minimize my expected loss. Okay? So one exercise I'm going to give you is a few lines, and it's and the result is very intuitive, that if I look at, so if X is distributed according to some distribution P, then I'm going to look at the expected loss when I'm trying to get for X, I'm guessing X with what would have been the optimal guess had X been distributed according to Q. Okay? Versus my expected loss if I do the optimal thing, namely, I make a guess which is optimal for the true distribution P. Okay, so this is obviously non-negative, because here I'm doing something suboptimal, and here I'm doing something optimal. But please show, as an exercise, that this is no more than some constant that depends on the loss function in question, but times the total variation distance between P and Q. Which is very intuitive, because if Q is close to P, then if I do something that would have been optimal, if X were distributed Q, Q is kind of close to P, then I can expect that my performance will be close to the optimal performance. And hypothetically, because of Pinksford's inequality, we know that this is more than, this is upper bounded by this constant times 1/2 the relative entropy. Okay, so bottom line, if P and Q are close and the total variation and the relative entropy, then your expected loss, if you give the Bayes response to Q, it's going to be pretty close to the optimal. And so now let's talk about prediction. So a predictor, okay, so a general predictor called F is the sequence of functions ft, t, 1, 2, 3, and so on, where ft is x Cartesian product, t minus 1 fold Cartesian product into an estimate. Okay, so ft, so basically, so ft takes a t minus 1 tuple, the past t minus 1 components of the sequence, and gives an estimate of x at time t. Okay, so if you give me, so let's say you gave me your loss function, interest, right? I can look at the loss incurred when x time t is something, xt, and you're using a predictor, f, which is going to predict for xt the value ft based on the x's up to t minus 1. Okay, so this is, so let's say now if I have a prediction problem, right, I'm going to come up with a predictor. It's cumulative loss or cumulative normalized first symbol, first time step. Loss is going to be this. Okay, and now I can talk about okay, and so I can also talk about if so if now my data, now let's, instead of this sort of one-shot problem we had here, let's talk about sequential prediction problem. So you have the data, the process of interest, x1, x2, and so on. So now it's a process that you want to predict, and that has some law, so it's distributed P, so P is now the law process. Then we can talk about the optimal predictor, right? So I can talk about, I can look at 1 over n sum t from 1 to n L xt, ft, x t minus 1. Right, so I can talk about, I can have a number expected for per symbol loss of a predictor F, and I can ask to minimize this for all predictors in the world. Okay, and let's denote by F, let's superscript it by P, by the law P, to be the optimal predictor. So I give you a law on process P, let FP be the optimal predictor that will minimize the expected life yielded loss. Okay, so additional exercise I'm going to give you, and not very difficult given this definition of the Bayes response, is that you can be very explicit about this predictor. So the optimal predictor, if your process has law P, is the predictor that predicts for time t. Okay, based on what it has seen, on the past sequence that it's seen, it's simply the Bayes response to a conditional distribution of what it is that you're trying to predict or to guess. So the conditional distribution of xt given what you've seen. Okay, as induced by the law of P. So again, this is not very hard or deep. Simply, right, if you want to minimize this expectation, you can be very greedy about minimizing for every time step t the expected loss, the prediction for time t. And that expected loss is simply an estimation problem, right? You want to estimate or guess the value of xt given what you've seen so far, which is the x of up to t minus 1. Up to t minus 1, just a one-shot problem where you want to sort of guess the value of xt. And it's distributed according to the conditional distribution of xt. Right? And so the best thing to do is, by definition, the Bayes response. It's a one-shot problem. Okay, and so now what I want to do together is derive the upper bound that I have here, which is, so hopefully you saw this, you with me, and you take a picture, because I need another word. So I'm just going to try to bring this around. Yes? Oh, okay. Okay, so now let's look at what we have on the slide, which is, you give me a, so I want to look at the expected normalized cumulative loss of a predictor. So let's say, so again, I'm assuming that my data to be predicted is governed by some law P. Okay. And I am going to predict using a predictor which is optimized for some possibly other law P. Okay? So this is my normalized sort of per symbol, per time step loss, expected loss. All right? How does it employ the optimal predictor for this process, which is the predictor optimized for the true law P. Right? So let's see what we have. We have 1 over n, sum p from 1 to n, expectation of the loss xt f t. In fact, let me already write down what this FTQ is. So the FTQ, right, according to the exercise, is in fact the phase response. Is in fact the phase response to the conditional distribution of xt given the past x's under Q. Right, and this guy is same thing. We're going to have the phase response to the true law on xt given the past observations. Everyone get this? And let me in fact use iterated expectations. So let me add this expectation. An expectation first, conditioning on x up to t minus 1, and then take an outer expectation over the condition here. Now, what can I say? Inner expectation. How can I upper bound it in terms of something that you would have been at the beginning if we had seen the previous board? Right, to recall what was exercise 1. Right? Exercise 1 showed us that for this one-shot estimation problem, and in fact, look what we have here. So here, right, what we have is a one-shot estimation problem. So given the past x's, what I'm trying to do is estimate one symbol, right, x at time t. And here I'm using the phase response for sort of some distribution, q of xt being minus 1. And here I'm giving the phase response respect to the true distribution, right? The true distribution on xt given the xt minus 1. So this is exactly, we're exactly in this one-shot scenario from exercise 1, where the role of that generic x is played by xt, the role of that p, the distribution on one guy, is played by this distribution, this p on xt given these guys, the role of q, p on xt given these guys. Right, and that exercise told us that this is upper bounded by some constant that depends on the loss function, and then we have a half relative entropy. So between what? Between p on xt given xt minus 1 and q xt given xt minus 1. So is everyone with me that this inner expectation is bounded in this way by just a direct plug and play from exercise 1? Oh, thank you. Right, we got the square root. And just like in Matthew's lecture, note that this really is a random quantity because these guys, the x up to t minus 1 that I'm conditioning on are random. I haven't yet taken this outer expectation, right? But now take this outer expectation over these guys that I'm conditioning on and use the fact that right, square root is concave. So now let's use Jensen, and we're going to get this whole thing, right, will be upper bounded. So I'm going to constant CL, and then I'm going to go with this outer expectation inside of the square root. And by Jensen, I have an upper bound, which is 1/2 square root 1/2 the expectation of this, right? Which now I'm going to use automatically my notation. You're going to Kerner, which is the expectation of this, right? So the way I denote it is relative entropy between P xt given the task x, Q xt given the task x, then average over the true log, what condition on here. Okay. And in fact, let me use Jensen yet again. So, okay, so what do I have? I have this as CL is here, sum T from 1 to n, 1 over n, 1/2 relative entropy P x T given x minus 1, Q x T given x minus 1. C minus 1 square root. Okay, so again, let me use Jensen. Think of this, and here I'm averaging. This is T from 1 to n, 1 over n. So now it's a different sort of expectation or average. Averaging over square root of something. Again, by Jensen, I can put this average inside of the square root, and further upper bound by CL square root of sum P from 1 to n, 1 over n, relative entropy P xt given xt minus 1, Q xt given xt minus 1. Now, recalling the chain rule for relative entropy that I mentioned at the beginning of the previous lecture, you can tell me what, put the 1 over n here. So what is this? So this is nothing but the relative entropy between the law, the true law on the n tuple and the law under Q of the n tuple. I think I lost the factor of 2. I have 2 here. So 2 something. So constant over there is different. But okay, but this is what I wanted, the one thing I wanted to do together. So we won't say everything is on the slides. But it also gives you sort of a sense of the kind of analysis and math that goes on, and that's also kind of similar to the math that underlies some of the results that I'll now state without proof for directed information estimation. Okay? But I guess one of the take-home messages here is that, if you have a universal compressor, or equivalently a law, let's see, a law induced by a universal compressor, which is a law Q, for which this normalized relative entropy is guaranteed to vanish, right? That it induces universal schemes for other problems, such as prediction. Because what this upper bound is telling us, that if you take Q, a universal Q, again, induced by a universal compressor, and now you look at the predictor that it induces. Okay, so we predict according to what would be optimal under Q. Then your prediction performance is going to converge to the optimal prediction performance. Say if the Q is universal with respect to all stationary processes, you're guaranteed that your predictor is a universal predictor with respect to all. Okay? And again, also computationally, algorithmically, often it's the case, certainly with LZ, CPW, that there's also a very nice graceful, if the compressor is graceful, then the induced sequential probability assignment, and therefore the induced predictor, will be equally graceful. Compute. This is for prediction, by the way, and this has been used. You can look up a site by Emin Martinian. I believe it's still up. He's a former student at MIT quite a while back. But the website is still up. It's the Universal Rock, Paper, Scissors player. And basically, what he does is he implements the predictor, which is induced by the Olympic Z compressor for a sequence over the alphabet, the ternary alphabet of rock, paper, scissors. Basically, you play against this team. This team looks at what you've done so far. It's a sequence, it's a ternary sequence. Every time it's RPS. And then it gives what will beat what the LZ predict is the next draw of the play. And it actually turns out to be very cute. It does very well. And I tried to play against it and it beat me pretty well. Okay, so that's for prediction. And now let's get back to directed information estimation. So we want to, okay, so I'm going to give you just a flavor. This is the creature we want to estimate. So maybe I'll just touch on, we have several approaches based on these ideas. Let's look at, maybe we'll look at just two of the four. So one is, okay, this is the creature that we're interested in estimating. One way of expressing it is as the entropy of the Y. So mutual information, right? One way of expressing it is the entropy of the Y sequence minus the entropy of the Y sequence division on the X sequence. In the case of directed information, this conditional entropy is a so-called causally conditioned entropy, which is the sum of the H, Yi given the path of Y's, and what I'm conditioning from the X, it's not the whole X, but the X up to I. This is a so-called H causally condition. Y sequence, H of Y causally condition on X. So if you eyeball this thing, there's one estimator that sort of very naturally suggests itself to estimate the entropy of the Y sequence using your favorite entropy estimator. For example, take a universal compressor, employ it on the Y sequence, see what its normalized code length is. That's going to be a good estimate for the entropy of Y. And then for this, the causally conditioned entropy, here's one thing that's very natural to try to do. I'm going to basically, so recall this H of Yn causally conditioned on Xn is, by its definition, it's minus the sum of the expected log of the true P of Yi given Yi minus 1 in Xi. But I don't know the true P. What I'll do is I'll use a universal Q, a universal sequential probability assignment, and I'll see what the probability is that it gives to Y times I given the past Y's, and the X is up to I. Okay, so I'm slightly, maybe I should be slightly more specific and explicit here. What I mean really by this is you take a universal Q and you run it on the sequence of pairs. Okay, so now your sequence on which you employ Q is the sequence Xi, Yi. And so you run it on sequence of pairs, it's going to give you say, a Q on the pair xi, yi, given the past x's and y's up to I minus 1. So it's a joint, and then you sort of marginalize it properly, and you get a posterior on say, yi given xi and the past x's. So that's what you do here. And what you can show, and so you may sort of hope that if Q is universal, and this thing is going to be close in some sense, with some probability, to, again, the expected value of this when you use the truth. And this is something that you can show with an analysis kind of similar done here together for prediction, and you can get something of this nature. So if Q is any universal probability assignment, and xy is any jointly stationary ergodic pair of processes, then this estimator that we've just shown will converge to the direct information rate in L1. And again, all amongst for any jointly stationary one. If this Q is also pointwise universal, they're about almost sure convergence, then this one will also almost sure. So this is one result you can get. There's also, if you assume a little more about this Q, if you assume a little more about the process, not just any stationary ergodic, slightly more like Markov, giving more mixing rate, then you can also get very tight rate of convergence. And essentially, you can show you the best rates of convergence. Let me just show you. So here's one example on. I'll spare you the details. This is simulated data. This black line is the ground truth, the true direct good information rate, and you sort of see how this. And these are sort of few realizations. You see how the estimate eventually converges to what it needs to converge, and also you can actually show that you can see that it converges in the right rate. Central still depend. Let me quickly show. This has some advantages, some disadvantages. For example, because we're estimating separately the entropy of Y and this causal condition entropy, we can get all sorts of weird stuff for small samples, such as a negative estimate, non-negative, and so on. One of the remedies, I'm going to spare you the second approach. We can do something like that. Let me just give you one additional approach to remedy the fact that the estimate in the previous approach could, in principle, also be negative. So one way, if you recall, expressing the neutral information is as a relative entropy between between this guy, given this guy, and the distribution only on this guy, and then the average over the distribution of this guy. So we have the same thing, the same formula here, where everything is conditioned also on y of y minus 1, and then average with respect to that. Okay, so this term, the sum that defines the direct information, is really a sum of such relative entropies. And so, as you can imagine, what's very natural here to do is replace the unknown P with a universal Q. Replace this unknown P also with a universal Q. And basically let sort of time take care of the averaging that this P is doing. And what you get as a result is this estimate. So you're going to look at, you're going to employ one universal Q on the sequence of pairs. And then from that Q, you're going to induce the Q on Y, the distribution on Yi, given the past Y's and the past to present X's. You're going to compute the relative entropy between that and the distribution under a universal Q employed only on the Y sequence on the I component of the Y sequence given the past. And that's basically, that's going to be your estimate. And you can show sort of similar results about convergence. In practice, it comes out, first of all, it doesn't do weird stuff, such as giving negative values, regardless of how small your sample size is, because it's always a sum of relative entropy. And also in practice, we're seeing better, so less erratic behavior and better. So let me kind of, I guess I'm very close to being out of time. So let me, and so you can do all sorts of similar, kind of similarly flavored ideas, and you can get all sorts of variations on these themes. And you can also sort of combine between them. But the bottom line is that you have, you give me your favorite universal compressors. Let's say, by the way, in our case, the Q that we use is the one induced by CTW. And we have all these approaches that are based on this universal Qs for estimating the direct information rate. So again, this is for simulated data, where we know, I won't go into detail, but basically we know the ground truth, so we can compute the directed information from y to x. So black line, direct information from x to y. It's this black line, it's the direct information from y to x. This is direct information from x to y. And this is the sum, which is the overall mutual information. And we're seeing that these estimates are pretty much nailing it. And this is for simulated data. So one last example I'll end with. For example, we want to maybe invest in Dow Jones, and we want to know to what extent you should be looking also at the Hang Seng Index when you do these investments. Okay, so if you look at, so this is real data plotted here on a daily basis that we took from Yahoo, the Yahoo website in 1990-2010. You look at this thing, and it's kind of pretty clear that these signals are somehow correlated, statistically dependent. But again, that's not the point. What you want to know is, to what extent, say, I should be looking at everything that happened with Hang Seng so far if I want to now do some investment or do some inference on the next thing that's going to be happening with Dow Jones, right? And then, by the way, this fits perfectly to this sort of scenario that I showed you, where I'm assuming x1, then y1, then x2, then y2, and so on, because of the time difference, which I'm now feeling very painfully, between New York and Hong Kong. When one is open, when one stock exchange is open, the other is closed, and vice versa. So exactly the setting. And so when you actually run the directed information estimates that I've shown you, again, the details vary, but very consistently, you see under all of these estimation approaches the same qualitative phenomenon, which is that, in fact, most of the mutual information is in the directed information from Dow Jones to Hang Seng. Right? So at least from 1990 to 2010, Dow Jones was the influential driving factor. It was driving and sort of very much responsible for the evolution of what happens in Hang Seng, and very, very, very little effect in the other direction. Basically, if I'm doing investment on the Dow Jones, I really don't need to look at anything that happened in Hang Seng. That was the case up to 2010. This is probably, we now go to 2030, ask me in a few years, probably it's not going to be a single conclusion. But in any case, this is what we found. And You can of course think of more sophisticated applications. Now you have maybe a multitude of stocks, a portfolio. You want to know, you want to do inference on one. You want to know which of the others are relevant. So you can compute these information and then see, and then maybe take those that are most relevant and then fit a model that uses only those for doing prediction on the stocks that you care about. And one of our former students is in the financial industry. He said that if he tells me the details, he's going to have to kill me. But he did allude to the fact that he's been using this stuff very lucratively. Just to do some motivation. They will pick it up from here on.
That is another reasoning for the word mutual information, mutual funds, mutual information. Maybe they should be called directed funds. Question from the audience? So, in terms of, so here you looked at the estimation, so compression and leading to prediction. I guess you could extend it to sort of the Cover's universal portfolio framework, and also put in how does the answer change if you have sort of expected profit on a step-by-step basis?
Right. So kind of formally and generically speaking, Cover's universal portfolio framework is really just one special case of sequential decision-making under a loss function. So in his case, it's a very specific loss function, very specific sort of action space. And so you could envision asking yourself, what would be, for that loss function, that action space, what would something like lentil zip induce? I should say, this is also a detail that I swept here under the carpet. The derivation of the direct information estimates and sequential probability assignments that are induced by universal compressors, these are all good for the classical regimes we know, finite alphabet and n large. Financial data is essentially continuous. As is the case in Cover's universal portfolios. What we've done here was, very brute force quantization through just a few levels, and then employing the direct information estimates. You could probably do things that are more sophisticated, and so also in the context of universal portfolios, you would have to think about probably more sophisticated ways of perhaps quantizing than doing things like this, or doing overall more sophisticated things that treat more directly the continuous, the analog nature of the data, such as all sorts of kernel density estimates, and so on. But then you're deviating from one of the main themes that I'm trying to convey here, which is let's try to take a lot of the know-how from compression, lossless compression, finite alphabet, large N, and sort of see what it does. So for that, the best that I can come up with is just quantize and then plug and plug. But for sure, people in, say, in the financial industry, they try, they work very hard and they try every approach, and in fact, they try to be sort of non-standard. They don't want to use the usual statistical methodologies, and so they try to pick up everything in the literature, and I'm sure that many people have done the universal portfolio a la Cover, and used many things that are way more, that are probably more sound than quantize and plug and plug.
Any other questions? So I think here you showed that if you have a code units, so compressor you can use it for prediction. Is the other way also?
So strictly speaking, the answer is no. And sometimes you can come up with very stupid, sort of degenerate loss functions with respect to which essentially any predictor would be optimal. There is, so, and on the other hand, there is a sense in which this is true. So in fact, universal or compression is really equivalent to sequential probability assignment under logarithmic loss. And getting back to our, so you might say that for universal compression is equivalent to universal prediction under log loss, and therefore you can do this as saying that if you come up with a universal predictor under log loss, then it induces a universal predictor under any loss function. So that, in a sense, is another strong justification for the canonical nature of the logarithm loss function.
Any last questions? Let's thank Tsachy. So a couple of quick announcements. So as you know, today we're going to be going on an excursion. So it will be hot. Yeah. So the t-shirts that we are giving you are, they're very nice at absorbing sweat and all of that. So you may want to change into that. Even if you don't, we would like you, at least for now, to wear those shirts because